2,300 years ago, a Greek showed that the number of primes itself is not a number. 2,000 years later, a Prussian demonstrated that there is no largest prime. 2 years ago, a Croatian proved that there are infinitely many prime numbers. All those mathematicians proved the same statement, and they are not alone, as Euclid's theorem has over 180 different proofs. But why? Why do mathematicians spend their time reproving the same theorem over and over again? After all, that doesn't make it more true, so why care? And Euclid's theorem is not alone in this regard, as whole books were written about Pythagoras' theorem. Further, the law of quadratic reciprocity has over 200 different proofs. To understand why those mathematicians did not stop, we have to study their work. For this, we will look into 3 different ways to prove that there are infinitely many prime numbers, to see what makes each proof special. We start with Euclid's original proof that is known since ancient times. It's a proof by contradiction, meaning that we start by assuming that there are only finitely many primes and show that this assumption leads to a contradiction. If there are only finitely many primes, then we can write them down as a list, where p1 is the first prime and pn is the last one. We use this to define a new value n that is simply the product of all primes plus 1. We will now consider 2 different cases. First, we assume that n is a prime. Note that n itself is larger than all values of our list, so we found a new bigger prime number. This contradicts our assumption that the list contains all primes since n is not part of our list, so this case is not possible. Second, assume that n is not a prime number. Now, by definition, n is a product of 2 numbers that are both not equal to 1. For those numbers, we can again ask if they are prime or not. If a number is not prime, then we can split it up further. However, at some point, we have to reach a number that cannot be split up, meaning that we found a prime. Because our list contains all prime numbers, we get that this number must be equal to some pj that is part of our list. So pj appears in the product of n, and therefore n is divisible by it. But now look what happens if we actually divide n by pj. What we get is 2 parts. In the first part, pj just cancels out, so we end up with a product of prime numbers, which is therefore some natural number. Let's call it m. The second one is just 1 over pj, which is strictly larger than 0 but less than 1. So we get a value that lies between m and m plus 1 and is therefore not a natural number itself. This means that pj does not divide n, which is a contradiction to the fact that pj actually divides n. So both possibilities lead to a contradiction, which means that our original assumption that there is a finite list containing all prime numbers must be wrong. Pretty neat. The British mathematician Hardy wrote about this proof in his book A Mathematician's Apology. The arguments take so odd and surprising a form. The weapons used seem so childishly simple when compared with the far-reaching results. But there's no escape from the conclusion. There are no complications of details. One line of attack is enough in each case. A mathematical proof should resemble a simple and clear-cut constellation, not a scattered cluster in the Milky Way. Even though mathematics often looks quite complicated, it is actually a science that longs for simplicity. As John Conway puts it, people think mathematics is complicated. Mathematics is the simple bit. It's the stuff we can understand. It's cats that are complicated. This simplicity is what makes Euclid's proof in the eyes of Hardy beautiful and worth preserving, as there is no permanent place in this world for ugly mathematics. For people like him and Conway, mathematics is actually an aesthetic subject almost entirely. So let us consider another beautiful proof, This time it was discovered by the famous mathematician Paul Erdős back in 1938 when he was 25. This proof is much harder to understand, but let's give it a try. Again, we start by looking at the set of all prime numbers. This time, we take the inverse of each of them and sum them up. Now, assume again that there are only finitely many prime numbers. If this was the case, then we get a sum of finitely many values, meaning that the whole sum is finite too. However, we will prove that the sum is actually infinite, meaning it contains infinitely many terms, and therefore there are infinitely many primes. Our proof is again by contradiction, so we assume that the sum is actually finite and converges to some value x. Look what happens if we start the sum with the second term instead. We obtain the smaller value x minus 1/2, and if we start with the third term, we get an even smaller value. If we keep moving to the right, then our values become smaller and smaller, and at some point we are getting to a k such that starting from k plus 1 yields a sum that is less than 1/2. We don't know k, but we know that it exists as long as our sum is finite, so let's give it a special color. We use k to split up our primes by calling the first k ones small and the remaining ones big. Next, we look at the set big N of numbers from 1 to n. Currently, this n is just a placeholder for some number that we will pick later. The idea of the proof is to partition this set into two smaller sets based on the big and small prime numbers. We say that a number in big N belongs to NB if it's divisible by at least one big prime number. On the other side, the set in S is simply the rest, meaning it contains those numbers that are only divisible by small primes. This all might be a bit complicated, so let us visualize it with a small example. Say that k is equal to 3, so the set of small prime numbers is 2, 3, and 5, and all other primes are big. If we now choose n is equal to 15, then we look at the first 15 numbers. 14, for example, is divisible by 7, which is a big prime number, so it belongs to the set NB. However, the number 12 is only divisible by the small prime numbers 2 and 3, so it's part of an S. We can do this for all numbers in n and see that each number either goes to an B or an S. Thus, the size of big N is equal to the size of NB plus the size of an S. Our goal is to show that, assuming our sum is finite, the size of an S plus the size of NB is actually strictly smaller than the size of big N, which is a contradiction to the fact that they are actually equal. We start by considering the set NB and try to find an upper bound for it. For this, we start by creating a box for each big prime number. Each box contains all numbers that are divisible by its prime and are less than n. Now, if we take some element of NB, then it's divisible by at least one big prime and therefore part of at least one box. Of course, it could happen that an element is contained in multiple boxes since it could be divisible by multiple big primes. Still, each element is in at least one box, so the size of NB is at most the size of the sums of all boxes. If we look at a specific box, then it contains the values 1 times bj, 2 times bj, 3 times bj, and so on, until we hit some q times bj that is just below n. If we rewrite this a bit, then we see that q is at most n divided by bj, which is an upper bound for the box size. Next, we plug this into our upper bound and pull out the n. Remember that we pick the big primes in a way such that the sum over the big primes is less than 1/2. Thus, the whole expression is less than n over 2, which is an upper bound for nb. To upper bound the size of an S, we use a different approach. For this, we first show that each x in an S can be decomposed into an A part with some special properties that we discuss later, and the square of some remaining B part. Like in the proof of Euclid, we start by splitting up our value x further and further until we get a product of only prime numbers. By definition, each x in an S is only divisible by small primes, meaning that each prime number in the product is small too. For example, here x is a product of 5 different small prime numbers, and the exponent symbolizes how often each prime appears in x. Let us stick with this example for a moment, but note that everything we do also works for all other numbers in an S in exactly the same way. The trick is to start ordering the prime powers according to whether the exponent is even or odd. Now, each odd number can be written as 1 plus an even number, which allows us to split them up further. We move the new even powers to the other even exponents, and what we get is a product where on the left side each prime appears only once, and on the right side each exponent is an even number. Each number on the right can be turned into a square number, which allows us to turn the whole right-hand side into a square. What we now get is that x is equal to some part that we call a times the square of some other part that we call b. Since this decomposition is unique for each x, we get that the size of an S is at most the possible values of our a parts times the possible value of our b parts. So let us upper bound both. Each ax is a product of small prime numbers, and for each of the k many small primes, we have two possibilities. Either the prime is part of A or not, meaning that there are at most 2 to the k many different ways for obtaining different A parts. On the other side, note that each x is at most n since it is part of an S. This, however, means that bx squared is also at most n, which implies that our b part is at most root n. So there are at most root n different b parts, and in total we get that the size of an S is at most 2 to the k times root n. To recall, we started by assuming that this sum over all primes is finite. Under this assumption, we can define the notion of small and big prime numbers, and for an arbitrary value n, we use this to split up the set of the first n integers into two sets ns and nb that together form big N. Further, we showed that nb is always less than n over 2, and ns is always at most 2 to the k times root n. Plugging this in gives us the following inequality. Note that at no point we assumed anything about n. Thus, if our assumption that the sum is finite is correct, we get that this inequality must be true for all numbers n. So what happens if we simply pick n to be 2 to the 2k plus 2? We start by simplifying a bit and then plugging in our value. By using some power laws, we then end up with 2 to the 2k plus 1 is strictly less than 2 to the 2k plus 1, which is a direct contradiction. Thus, our assumption that the sum was finite is false, meaning that the sum actually goes to infinity, proving that there are infinitely many terms and therefore primes. But Erdős actually showed something much stronger with his proof. He showed that in some sense the prime numbers are very frequent. For example, we know that there are also infinitely many square numbers, so how can we compare them with the primes? Let's look at the first 19 numbers. Among those, there are 24 prime numbers, but only 9 square numbers. However, this might be a fluke. How can we be sure that this doesn't change after considering the first 100,000 numbers or the first 1 billion ones? Both sets are countable infinite after all. To compare these infinities, we do the same with the square numbers what we did with the prime numbers and sum up all their inverse values. This time, the answer is not infinite but actually something finite, unlike what happened in the prime number case. So in a certain sense, there are much more prime numbers than square numbers. We can even go one step further and ask if there's always a prime number between two consecutive square numbers. For example, between 25 and 36, there are the two prime numbers 29 and 31, and between 64 and 81, there are 4 different primes. I mean, we just showed that the prime numbers are more frequent, so there should always be some prime between two adjacent square numbers, shouldn't it? Actually, this is known as the Chandra's conjecture and an unsolved problem since 1808. What we see is that Erdős proof leads to much deeper insights about the frequency of prime numbers. This proof goes beyond infinity and gives us an understanding that the primes are not just something that occasionally occur here and there. This proof also raises new questions that are unsolved up to this date. Our last proof was discovered by Furstenberg in 1955 when he was 20. It uses a completely different set of tools, namely topology. You may have heard the joke that for a mathematician, a donut and a mug are the same because they share the same topology. So let me ruin the joke for you by explaining what a topology actually is. Formally, a topology is any family of subsets of some base set X that are based on specific rules. Family in this case is simply a fancy name for a collection of sets, and the base set X could be anything you like. For example, the real numbers or the integers or anything else you can imagine. Now we say that our family of subsets tau is a topology on X if it satisfies the following 3 rules. First, tau must contain the empty set and the whole set X. Second, if we pick any family of elements in tau, then the union is still in tau. It's important to point out that we can unify any number of elements. Especially, we can take the union of infinitely many different elements in tau. Lastly, if we take any finite number of elements in tau, then the intersection is also part of our topology. Note that we only use finite intersections here. As a quick side note, the elements of a topology are usually called open. So let us look at some examples. The power set of X, that's just the family of all subsets of X, is a topology on X. By definition, it contains the empty set and it contains the whole set X. Also, the union and intersection of any family of sets is still a subset of X and therefore a part of our power set. On the other side, the family that only consists of the empty set and X itself forms a different topology on X. You may rightfully ask what this abstract nonsense has to do with transforming a mug into a donut. The point is that the definition is so abstract and general that it pops up everywhere in mathematics. The idea is that the open sets define some kind of geometry that allow us to define what it means to be a continuous map. This way we can describe how to deform objects, which is why we can transform the mug into a donut. The key word here is homeomorphism. So Furstenberg starts his proof by introducing the topology on the integers. For that, we define for all a and b the set NAB as the set of all y values of the line with slope a and offset b. Let me point out that we will only consider sets where a is not equal to 0 because that way each line has infinitely many different y values. For example, if a is equal to 2 and b is equal to -1, then we end up with all these values here, and you can clearly see that they are just the y values of this purple line. We now say that a set is part of our topology tau if it's some union of lines. To see that this really defines a topology, we have to check our three rules. First, the empty set is part of our topology since we can simply take an empty union of lines which yields the empty set. Further, the set of integers is equal to the line with slope 1 and offset 0, meaning that set is also part of our topology. Next, we have to show that any union of elements in tau is again in tau. Since this is a union of unions, we can simplify it to immediately get our result. Lastly, we have to check that any finite intersection of elements in tau is again in tau. And this is a small exercise for you. As a hint, try to convince yourself that it's already enough to check that any intersection of two lines is again in our topology. Now, to bring back the prime numbers, we show that this expression here is equal to -1, 1, where the intersection goes over all primes. To understand it, let us focus on a specific prime number p. Any number x can be written as a product with p and some remainder part that is between 0 and p minus 1. We get these values by doing integer division. For example, if p is equal to 5, then 34 can be written as 6 times 5 with remainder 4. In the same way, the number 16 can be written as 3 times 5 with remainder 1. Now this formula has exactly the same form as in the definition of NAB, which means that we can write down x in this way if and only if x is in NPB. But what happens if the remainder is 0? This means that x is a multiple of p, which can only happen if p divides x. Thus, x is divisible by p if and only if it is part of NP0. Now, this union here includes everything except NP0, meaning that it has exactly those numbers that are not divisible by p. With this, we have everything we need to understand our expression here. This intersection over all primes means that this condition here has to be true for all prime numbers. So this set is equal to all numbers that are not divisible by any prime. The only integers that have this property are -1 and 1, which proves our equality. If we assume that the set of all prime numbers is finite, then our expression turns into a finite intersection. Further, each union is part of tau by definition. Remember that the third rule of our topology states that any finite intersection of elements stays part of our topology, which therefore implies that the set -1, 1 is part of tau. This means that it must contain some set NAB. But by definition, each set NAB contains infinitely many elements, which would imply that -1, 1 also contains infinitely many elements, which is clearly not the case. Meaning, our initial assumption that there are only finitely many primes must be wrong, proving that there are indeed infinitely many prime numbers. Furstenberg showed with his proof that there are bridges between topology and number theory. When studying mathematics, one often has the feeling that it consists of many different small islands. There's one for topology, one for number theory, one for analysis, one for algebra, and so on. However, the most significant mathematical theorems are those that create bridges between those islands. They show us that we can leave our small world to venture out into new ones, to find those tools that we need. This project of linking mathematics together is arguably one of the most important projects in mathematics, and the proof of Furstenberg shows that he is surely a bridge builder. So why did we prove the same theorem 3 times? There is no simple answer for this. Euclid's proof is very simple, which makes it great for teaching, but this is also what makes it so beautiful. Erdős' proof, still being very elegant, is far harder to understand. It also yields more results, and this additional knowledge leads to new questions that still remain unsolved. Furstenberg's proof demonstrates that we can use tools from other parts of mathematics which might help us with proving other theorems. But like I said in the beginning, there are over 180 different proofs. Some of them are just nice and neat. Others may use a clever trick that might be useful somewhere else. Still others just expose a completely new viewpoint. This is best described by the following quote: "Any good theorem should have several proofs, more the better. For 2 reasons. Usually, different proofs have different strengths and weaknesses, and they generalize in different directions. They are not just repetitions." At the end, a proof is always more than what has to be proven.